Today we're going to begin talking about modern physics. Modern physics really began with the discovery that light can exhibit both wave and particle properties. They call this the wave-particle duality. Of light. We've seen before that light can act as a wave. We saw this when we were dealing with optics. Mirrors, lenses, diffraction, refraction, reflection, all of these different things showed that light acted as a wave. And it had all the different wave properties: frequency, wavelength, speed, amplitude, so on and so forth. One of the big things that we saw was when you passed when you passed light through a double slit. So if you had light coming in, like so, through a boundary. I actually got this backwards. Light should be coming in like this through a boundary. So plane waves. It would then do something along these lines, and it would bend, and because of that it's going to bend from this one, and it's going to bend from this one. And you see over here on your screen bright spots. I'll just represent with a dot. So if this was a laser, you would see a dot. Then you would see nothing, 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 and another dot, and nothing, 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 and another dot. So you would have bright spots and dark spots, and we had the equation that d sine theta equals m lambda, where theta is this angle here, d is the distance to the screen, or the slit width. D is the slit width, or the distance between the slits, I apologize. This was when you had L and X thrown in there as well instead of sine theta. So D is the distance between the slits, lambda is the wavelength of the light, and M is the integer that you count there. So here you see you've got a wavelength. Wavelength usually implies that you have a wave, because otherwise how could you have a wavelength? So we talked about all of these different types of wave properties of light. Well, now we're going to start talking about the particle properties of light. And I will probably spell particle about 12 different ways. So the particle properties. The first big experiment, quasi-experiment, was more of a, there were some experiments into it, but enough on that. The first idea, I guess is the best way of putting it, is using black-body radiation. Okay, well, what is a black body? A black body is an object that will radiate in all frequencies of light. So an example of that is the sun. Our sun will give off energy in all of the light spectrum. So that goes from X-rays and gamma rays all the way down to radio waves. Now, it doesn't give off all radiation at the same rate. That meaning, if we look at a graph here of the intensity of radiation versus wavelength, lambda, you'll see in basically every black body radiator this going from 0 wavelength up to infinity, some type of shape that looks like that. Now the peak could be in different places. It could be a wider peak, a shallower peak. It might not go up as high if it's not a very intense black body radiator. But every black body radiator will give you a shape something like this. Our sun has a peak in this general region that is between yellow and green light. So that's somewhere on the order of 500 nanometers, give or take 100. Now, as a quick aside, what do you think this means for us? Well, since you can't answer me, I will answer. Our eyes have developed so that we see green and yellow light very, very well, which is why a green laser pointer can do a lot more damage to your eyes than the red one can. Given that they're the same power, the green laser pointer will hurt your eyes more because your eyes are more sensitive to the green laser pointer, which is why I tell you to be very, very careful when you're using one. So that's what a blackbody radiator is. Now, why does blackbody radiation itself give rise to wave being a particle? I mean, it looks like you have various wavelengths of light. Well, the problem is, if you look at the energy that is given off by the sun, or really any blackbody radiator, I'll use the sun because it's a pretty easy example to look at. The energy needs to be finite. If it's not, the universe would die. Well, not really die, but it would explode, because there would be an infinite amount of energy from every given blackbody radiator. At the time, when light was just a wave, people had a lot of trouble with this, because this graph here showed that regardless of how far you go out here, there will be some small intensity of radiation, which means that you're going to have an infinite amount of energy given off by the sun with this category. But people came in, Max Planck, and he said this can't be right. So there's got to be something different. And he said light is going to be quantized. Now, he didn't actually say that. This is what happened. He found that light was quantized. Now, what do I mean when I say quantized? Quantized means discrete. Discrete as in that it is packets. So you can't have light with any energy that it wants. Light only comes in very discrete amounts of energy. That energy, they showed, was equal to Planck's constant, which we're going to talk about in a minute, times the frequency of the light. Times an integer number n. So n can be any positive integer, 0 through infinity. So this is saying that only specific frequencies are allowed to give off light. Now, Planck's constant here, h, is equal to 6.63 times 10 to the negative 34th joule seconds. So when you look at this, you have frequency inverse seconds, h is in joules times seconds, so your energy will be in joules when using this equation. So, this is our starting off point. In almost every modern physics problem we see, we will have Planck's constant. This has been shown many, many times to be a good value. There's a couple of different experiments that we'll talk about where they come out with Planck's constant as the correct number. if you take physics in college, one of the labs will be showing that this is true. Now, we don't have all of the equipment to do this lab, so we're not going to, but in an actual college setting, you will do this lab, probably in your second semester. So that is a very brief introduction into the wave-particle duality and black-body radiators.